going to continue with the same theme, okay, that is okay, so we're going to continue the same theme, that is the motion of particles through a fluid. So however, we are going to look at the case of non-Brownian particles, okay, that is the particles that are much larger in size, okay. So it turns out that the motion of larger particles, okay, there's non-Brownian particles, is kind of you come across this in a lot of processing operations, okay. Any examples? So can you think of some examples where you come across motion of particles in a fluid? So when you consider an operation such as, say, removal of, say, dust, okay, dust particles from air, okay, or you could also have a case where there's a flue gas, okay, which is coming from one of the industries, right, and if this industry could be carrying a particle, okay. So in general, the particle that we are going to consider, like other cases, it could be a solid particle, it could be a liquid drop, okay, or a gas bubble, and again your fluid can be either air or a liquid, right, or a gas or a liquid, okay. So there are several operations, okay, in which you have particles moving in the fluid. One example could be, as I said, the removal of dust particles. You could also have cases where you have like, say, solid particles in a waste, okay, waste fluid, and if you want to like, say, discharge the waste liquid, you may have cases where you would like to recover particles from liquid waste. Plus you also have cases where in a lot of industries which produce acid, okay, you have acid mist, okay. Mist is basically fine droplets, okay. This is basically acid, and before you exit a mist into atmosphere, you would have to recover this droplets from the the waste, okay. So there are a lot of cases where you do come across motion of either solid particles, liquid droplets, or gas bubbles in the fluid, and therefore whatever we are going to do today is going to be of interest in that context of some of these operations, okay. Now whenever, so we said that when you think about okay, I have some issue with the let's see if we can do that. Yeah, okay. So now, so when you had fine particles, right, we kind of saw that there the particles were moving by themselves, okay. Of course there was a thermal energy because of the presence of fluid, okay, but in a sense they were moving by themselves. But whenever you look at larger particles, what you need for the particles to move is an external force, right, okay. And this external force can either come from density difference, okay, that is the density difference between the particle and the fluid, okay. So can you think of an external force where the density difference can be exploited to move the particle under consideration, right? Can you think of an example? can you think of an external force where I can exploit the density difference to affect the motion of particle in the fluid? Gravity, right? Okay, so your gravitational force is an example of a case where I can actually exploit the density difference to set a particle, in a fluid to move. Okay. Any other example where I can exploit the density difference for setting a particle to move? Was that osmosis? Why is osmosis related to density difference? Okay. Osmosis is basically typically you have some kind of a permeable membrane, right, where you can look at separation in terms of so there could be a membrane which is permeable only to some species, right? So in that context you can use that. But can you think of centrifugal forces, right? I mean, okay, centrifugal force is again one force where I can actually exploit the density difference. Any other external force that we can think of? Again, something that we discussed the other day. It could be electrical forces, it could be magnetic, okay, or it could be thermal forces, right? So essentially, so you can set a particle into motion by using any of the external fields. So we're going to see some examples where we're going to look at the motion of a particle under the influence of gravitational force and centrifugal force in this class. Okay. Now, so we'll think of a simple example. Okay, so let's think about a simple example. So I have a, like say, a column, okay, and this column is filled with fluid, okay, and let's say that the density of the fluid is rho, the viscosity is mu, and I have a particle to begin with, maybe sitting right at the top of the column. I'm holding it, okay, and let's say that the mass of the particle is m, and rho p is the density of the particle, okay, and then I just let the particle move down under the influence of some external force. So let's say that the external force that is acting on the particle is Fe, okay. So whenever a particle is set into motion, okay, say that there is an external force that is acting on the particle, say that is Fe, okay. Now we have kind of discussed in the class that whenever there is an external force which sets the particle into motion, there's always going to be a drag force, right? Okay, whenever there's a relative motion between the particle and the fluid, a drag force comes into picture. Okay, therefore there's going to be also drag force acting on the particle. Okay, now when the particle enters the fluid, it is going to displace some fluid as well, right? Therefore there's also going to be buoyancy as well, right? There's going to be Fb, this is your external force, this is your drag force, and this is your buoyancy, right? Now what you can do is you can think about writing a simple force balance, okay. So you can use Newton's second law, okay, that is your F is equal to ma, okay. So can we think about the direction of each of these forces? So if say that the external force is say acting down, so if you have now that you consider a particle in a fluid, so you have, maybe let's make it simpler. So I have a particle in a fluid, okay, this is your Fe, which is say acting downwards, okay. What could be the direction of Fd, which is the drag force, is going to be acting up, right? That's your Fd, because we know that the drag force opposes the motion of the particle, okay, and typically it acts in the direction opposite to the external force, and of course its direction is it's going to be parallel to the external force as well, okay. And buoyancy. So because the fluid is being displaced up, right? Therefore, your buoyancy is going to be acting in the upward. Somebody has a question? So it's going to be acting up, right? So therefore, my force balance basically becomes F E minus F D minus F buoyancy. Now, that is mass times acceleration. Okay, if the particle is moving with a velocity v, okay, if you have a particle in the fluid and if it is moving with a velocity v, okay, your acceleration is dv by dt. Okay, now in general, your Fe, which is the external force, I can write this as some mass times some acceleration Ae. Okay, that Ae would depend on the type of external force that you're considering. If you're going to consider gravity, it's going to be m times g, right? And if you're going to consider the centrifugal force, it could be something else. Okay, right? Therefore, I could write m times Ae, that is your external force, minus Fd. How do we get an expression for Fd? We'll go back to the definition of the drag coefficient. Okay, so we had said that your CD is Fd divided by AP, okay, divided by rho u square by 2 now, because rho v square by 2 now, because v is a velocity which the particle is moving. Okay, therefore, I can write Fd as CD times rho v square by 2 times AP, right? That's your, right? That's your the drag force. Yeah. Therefore, what I can do is I can substitute for these in the expression, and I can write, sorry with that. Okay, m times Ae minus CD times rho v square by 2 times AP minus, so you have a buoyancy, right? Fb. So this you actually obtain from the Archimedes principle, right? If m is the mass of the particle that you're considering, m divided by rho p, okay, is going to give me the volume of the water that the particle is going to displace. What is that? Rho p is the density of the particle, right? Times rho, which is the density of the fluid, that's going to give me what is the mass of the fluid that is displaced, times the external force, external, Ae, which is the acceleration because of the external force, is what is going to be your Fb. Okay, therefore, I can write this as m divided by rho p into rho times Ae should be equal to m into dv by dt, right? So I can do a little bit of rearrangement. Okay, so therefore I can write this as Ae, okay, that's here, okay, and as well as here, okay, times rho p minus rho divided by rho p, okay, minus CD times rho v square by 2 times m. I'm just dividing everything by m, okay, that into AP is going to be your dv by dt. Yeah. Now, this particular equation, okay, it is the Gowning equation for something called as a one-dimensional flow of particle through a fluid. Okay, and the reason why it's one-dimensional is because you're basically considering a particle which is moving in a direction where the direction of motion of the particle is parallel to the direction of the external force and the buoyancy. Okay, but however, you may have cases where that need not be the case. Okay, you could have a case where, let's say, a simple case of, instead of having a particle settle in a column of fluid like this, okay, if I tilt the column itself, okay, and if the particle is still settling under, say, the action of gravity, for example, then your the direction of motion will not be parallel to the direction of the external force and the buoyancy. Okay, in such cases, your particle will not move in a one-dimensional fashion. It could be moving in a two-dimensional fashion or three-dimensional fashion. That depends on the kind of the problem that you're trying to work with. At least in this case, we're considering a case where the particle is, like, say, in the case of gravity, it's dropping down. Okay, then the external force is basically acting, external force as well as the buoyancy is basically acting parallel. Okay, the direction may be different, but they're acting parallel to the motion of the particle. Okay, now it turns out that if you look at this expression, right, so I can simplify this further, right? If I consider the external force Fe to be a gravity, I can write this Fe to be your m times g, right? Or if you consider external force to be some kind of a centrifugal force, okay, it's going to be m times r times omega square, right? Therefore, I can substitute for these. I can simplify this further. Okay. One interesting thing to note from this equation is that if you look at, like, say, let's write this equation for the case of gravity. Okay, so that's okay. So for your external force being gravity, okay, your g times rho p minus rho divided by rho p is minus cd rho u square, rho v square by 2 times ap, and there's m here, right? That's equal to dd by dt. So if you look at, like, say, gravitational, the case of gravitational, settling of particles, or the flow of motion of particles and the gravity, this is your constant, right? Once you fix a fluid particle system, and once you fix the external force to be gravity in this case, okay, this is a constant term. Okay, that means if I go back to this example, right? So I had a particle. So the moment I drop the particle, okay, so this term is fixed, right? However, if you look at this term, right, because of the fact that the particle is going to accelerate, right? The particle is starting from rest. The moment I drop the particle, it's going to accelerate, because of which this term is going to go on increasing, right? Because this term goes as v square if the particle starts to go at a higher velocity. Therefore, this term is going to go up, go on increasing. However, this cannot increase forever, right? At some point, you're going to reach a case where this term would be equivalent to this term. Okay, so under these conditions, the particle is said to start moving in a fluid with a constant velocity. Okay, and because it's going to move with a constant velocity, your dv by dt is going to be 0, and this constant velocity is the maximum velocity that the particle can achieve under a given fluid particle combination. Okay, so therefore I can equate this to 0, okay, and get an expression for that constant velocity, which is what is called as which is typically denoted by ut, which is what is called as a terminal velocity. Okay, that means under the action of all these forces, okay, the particle that initially accelerates through the fluid, it is going to reach a constant velocity at some point during its flow. Okay, and that constant velocity is what is called as a terminal velocity. We kind of looked at the application of this terminal velocity concept when we looked at the measurement of viscosity of the fluid, right? We said that there's something called as if we looked at we looked at different cases of measurement of viscosity, right? There is some case where this is called as a falling ball viscometer, right? Do you remember that? Okay, there's something called as a falling ball viscometer, in which what you do is you make a particle flow through a fluid, okay, make it fall through a fluid, and then you basically exploit, okay, such one-dimensional equation of motion to really get an expression for that terminal velocity, and that terminal velocity, as we are going to see, is going to be related to the viscosity of the fluid in which the particle is moving, right? So people kind of use this concept to get the viscosity of the fluid in commercially available instruments for measuring viscosity. Okay, so let's do that. So let's let's equate this to 0 and then get an expression for, oops, sorry, oops. Okay, so can you tell me what is ut, right? So basically we'll go to the previous thing. So you equate, you know, this term g times rho p minus rho divided by rho p minus, okay, this, equate that to 0. Can you get me an expression for ut? Okay, so the conditions when the velocity of the particle reaches the terminal velocity, your u becomes ut. Okay, right? So that if you work it out, right, it's going to be something like this. So ut is going to be 2 times g into rho p minus rho multiplied by m divided by ap times rho p into cd by rho, right, something like that. That's your, oh. Can you try and get this expression? Okay, all I've done is basically equated that, you know, dv by dt is equal to 0. I've basically simplified. Okay, that's what you should be getting. Okay, now the equation that we wrote, right, it is kind of a general equation that is valid for objects of any shape. Okay, we really did not make any assumption that the particles are spherical or cylindrical or whatever, right? So the one-dimensional equation of motion that we wrote, right, let's go back. Okay, this expression or this equation is valid for particles of any size, you know, or any shape, right? So now what you can do is, you can now, if you're working with the particles of specific geometry, okay, I can simplify this expression further and I can actually get, right? So now if I want to work this out, like say if I'm considering a spherical particle, okay, we said that this AP, which is the projected area, we said that, you know, what you should do is, if you have a particle is moving in a fluid, you should look at a plane perpendicular to the fluid and you should look at what area do you see. Okay, if it's a spherical particle, your AP is going to be 1 over 4 pi dp square, right, where dp square is the diameter of the particle. Okay, I can substitute for AP. And what about CD? Okay, so what people have done is, people have done a lot of experiments, okay, and kind of tabulated, you know, the results of, you know, the measurement of CD, which is the drag coefficient, as a function of Reynolds number. Okay, this is the CD that we've been talking about. Okay, so that's your CD on the y-axis. Your x-axis is a Reynolds number. Okay, it turns out that if you look at this plot, there are two limiting cases. Okay, there's a case where if you look at the low Reynolds number case, okay, there's basically a line with a constant slope. Okay, this is what we kind of exploited in some of the previous examples, where we wrote CD to be 24 by Reynolds number, right? That basically corresponds to that Stokes law regime. Okay, it's what is called as a Stokes law regime, which is valid when the Reynolds number is less than 1. Okay, so therefore, if I'm working with conditions where the motion of the particle in the fluid occurs under the conditions such that the Reynolds number is less than 1, okay, for CD, I can replace this as 24 by Reynolds number. However, if you look at the case where, you know, the Reynolds numbers are larger, you know, for example 10 power 3 in that region, okay, there's a dotted line. That dotted line basically corresponds to a case where your CD is more or less constant, okay, and typical value of CD in that case is basically okay. So therefore you basically have two limiting cases, okay. This is CD is equal to 24 by Reynolds number, okay. That's for the case where your Reynolds number is less than 1, and you have another case where CD is 0.44, okay. That's for the case where your Reynolds number is typically greater than 1000, okay. Therefore I can exploit the experimental data that is available on particles of different sizes that have been done and tabulated, or kind of which is available in the form of CD versus Reynolds number plot. I can substitute for these limiting cases, and I can consider of course these are valid only for spherical particles, okay. The whatever plot that I showed, it's valid only for the motion of spherical particle in the fluid. If somebody is working with other types of particles, or other geometry of particles, you would have to think about using an appropriate CD versus Reynolds number plot, okay. Now that we've done that, so can we just replace, let's think about the case 1 where Reynolds number, your CD is 24 by Reynolds number, which is what is called as a Stokes law regime. Can you substitute for AP and CD and get me an expression for the settling velocity or the terminal velocity? Okay, let's do that for both for the Stokes law regime and also for the Newton's regime, okay, which is for cases where your Reynolds number is much greater than 1000. Can you do that and let me know what the results are? So I can actually write m in terms of the density of the particle and the volume of the particle, right? I can do that. So therefore this rho p gets cancelled, okay. Now of course I can express Vp in terms of the particle dimension, right? If pi dp cube by 6 is your volume of the particle, right? And of course I can substitute for AP to be 1 over 4 pi dp square, right? So if you substitute for all of that, okay, and of course your CD is equal to 24 by Reynolds number, right? So if you do all of that, the expression that I'm looking for is something like this, okay. This UT should go as G into dp square into rho p minus rho divided by 18 mu is what you would get for something called as a Stokes regime, okay. And your UT should basically go as something like 1.75 into square root of G dp into rho p minus rho divided by rho, okay. That's for Newton's regime, okay. which is basically a simple substitution, right? Okay, so you should be able to get this right. Yeah. Yeah, can you just work it out and let me know if you have issues with these things? Okay. Um, now it turns out that the concept that we have kind of discussed today, it's kind of useful in a lot of cases where people are interested to separate particles from a fluid. Okay, there's actually a process called elutriation. Okay, say that you have a powder sample. Okay, say that I have some sample that is given to me, which basically consists of powder, and say that the powder has particles of different sizes. Okay, now if the objective is to separate the particles that are present in the powder into different fractions, okay, larger size, smaller size, and stuff like that, what is typically done is you take this into some kind of a container. Okay, you fill the powder here, and what you do is you let basically a gas or any liquid. Okay, now what I can do is if I have a way of regulating, okay, if I have a way of regulating the flow rate of the fluid that I'm basically using, then depending upon the velocity with which the gas or the liquid is moving up the column, okay, depending upon the velocity with which the fluid is moving up the column, if the velocity of the fluid is larger than, okay, if the velocity of the fluid is larger than the terminal velocity of a particular particle, okay, that is there in the in the container, so either the particle is going to be carried along with the fluid or will continue to remain in the column. Okay, so therefore having an idea about the terminal velocity is also called as a terminal settling velocity, because when you're talking about motion of a particle under the influence of gravity, it's basically settling, right? So therefore, depending upon if you have an idea about whether the particles are kind of smaller or larger, whether the Reynolds number is less than 1 or more than 1000, okay, depending upon these conditions, so you should be able to come up with some estimate of what is the settling velocity of the particle. Now once I have an idea about that, basically by regulating the flow rate, okay, that is the velocity with which the fluid enters the column, I can actually regulate that to separate particles into different fractions. So therefore, if I want to remove particles of larger size, of course I would have to maintain a higher flow rate. Therefore, so this is one of the cases where the settling principles are kind of used for separation of particles by this technique called elutriation. Okay, we will look at some applications of this in the class when we do some tutorial problems. Okay, so any questions so far? Yeah. Mm-hmm. Correct. Mm-hmm. Mm-hmm. So typically when we said that when you start the particles, say that you start with the particle being at rest. Okay, I see a lot of people talking, so if you want to talk, you can leave. Okay. So say that you start with particle being at rest, okay, and let and you leave it and let it move under the influence of gravity. Now it turns out that the typical time that it takes for it to attain that terminal velocity is usually very small. Okay, in fact you have an experiment in the next semester. What you're going to do is you basically have a column, okay, something like this. Okay, what you do is you have some markers on the column. These markers are typically used to basically find out what is the distance that the particles travel in a given time. Okay, now what I can do is I can actually plot, okay, the velocity as a function of time. Okay, if you do that, you will see that, so basically what you do is in the experiment, when the particle basically enters this, you start a stopwatch. Okay, when it leaves, you basically stop it, right? I know the dimensions, the distance that it travels, and I know the time. I can basically plot it, right? So it turns out that, if you look at, of course, when you do this terminal velocity measurement, of course you don't look at that initial region, where the particle could still be, accelerating. However, it very quickly reaches the terminal velocity. Okay, so what one of the best way to do this would be, I look at velocity at successive intervals, and I look at, at what instant, the velocity between two successive regimes is constant. Okay, that's how people find out the terminal velocity. Okay, so yeah, I agree that, initially, there could be some case, where the velocity need not be terminal velocity, but typically you kind of work with a really large column. Okay, it's not that, so they basically the fluid that you're using for separation, it typically spends a reasonable amount of time in the residence time is typically larger. Okay, so in that time frame, the particle does attain a terminal velocity, and your separation is typically based on whether the velocity of the fluid is either larger or smaller than the terminal velocity of a given size. Okay, any more questions? No? Yeah. Oh, I just said that, your buoyancy, right? So this is basically based on the Archimedes principle, right? All you have to do is, I have a particle that enters the fluid that's going to displace some volume of the fluid. Okay, I should calculate what is the mass of the fluid that it is displaced, and times the acceleration, right? So your external, correct. So I only said, in this case, FB, I wrote it as m by rho p times rho into AE, right? Okay, typically you write it as m times g, right? Right. So in this case, g was the acceleration due to gravity. I said that, I'm going to use a general term AE, which is the acceleration for a given external force. That's all. Okay. So therefore, if I use gravity, your AE is going to be g. If I use, centrifugal force, is going to be r times omega square, right? That was the only. No, it depends on the external force which you're considering. For example, so when you use external, like say, when people use centrifugal forces, right? Typically, centrifugal forces are measured in terms of whether the centrifugal force is 1000 times g, 500 times g, and stuff like that, right? Now, when you do that, okay, you're really so if the acceleration because of gravity is very, very little, okay, then you're only talking about the dominant centrifugal force in that case. Okay, in such a case, your g has to come from the external force that you're using. Okay, though this weight concept, it's true only when you're talking about, or the buoyant force coming from the weight, right? It's only true only for the gravitational force. But however, if you use other external force, you would have to worry about the acceleration that comes from the external force. Yeah. Yeah. Yeah, correct, right? So now, no, I mean, it's the same thing, right? This is your mass that is displaced, right? M by rho p times rho, that is the mass of the fluid that is displaced by the particle, times your acceleration. Because m by rho p is the volume, times g is your mass, times the acceleration, right? Okay. Any other questions? So I would like you guys to go back and work at these equations. Okay, just write down this one-dimensional equation, put in appropriate terms. I would like you guys to derive those two equations. Okay, the Stokes law and the Newton's law. Okay, because we're going to use them for some of the tutorial that we're going to do later. Yeah. Yeah. But see, if I have, like, say, let's think about something like this. Okay, I have a, like, say, a plate that is rotating. Okay, now they say I put a fluid with some particles. Okay, now if you look at the relative, the I mean, so what you're trying to say is true when when you're the centrifugal force that you're using there, it becomes kind of comparable to gravity. Okay, however, if you take cases where you're really working at a very large rotation speeds, okay, so I think the motion, because of the gravity, you can actually neglect it. Yeah, and you would have to think about resolving it. You have to find out whether the gravitational force, the gravitational acceleration and the acceleration that is, because the different are in the same direction, or okay, you'd have to worry about resolving and then take appropriate components for your analysis. Okay, so you should also think a little bit about working out the equation that we developed also for cases of other particles. Okay, so we looked at a simple case of spherical particle, but however, you can also develop similar expressions if you're thinking about settling of, like, say, cylinder, for example. Okay, if I have a cylinder which is basically falling with this configuration, under the influence of gravity, then your AP, which is the projected area, that's going to be the area of a rectangle, right? Your length times the diameter. So you should have to take appropriate AP, right? Everyone agrees, right? So if I have a cylinder which is rotating, okay, so which is falling, so the area that is perpendicular to its flow is going to be the rectangle, right? That's your length times the diameter. However, if it is if it's basically falling with its axis, okay, in the direction of the external force, your again projected area is going to be same as the sphere, right? Pi r square. Okay, it basically sees a circle, right? So should be able to develop these equations for particles of other arbitrary shapes, and they should be able to work out the settling velocity expression. Yeah. Yes, it will, right? Because the plot that I showed for CD versus Reynolds number, it was written that it's only for a spherical particle case. Okay. However, people have done experiments on particles that are rough, irregular, again disc-like particles, cylinders, and stuff like that. Also you would have to worry about all of that as well. So even if you say that you have to think about the area that is in contact with the fluid, right? If you say that that's going to be, if you say it's 4 pi r square, right? It's going to be 4 times larger if you want to do it that way. I don't have an exact reason as to why it is done like that. Maybe I'll just think about it and maybe answer it in the next class. Okay, yeah. So the definition of AP is the area that the fluid, a plane that is perpendicular to the motion of the fluid, right? So if a liquid is flowing in a particular direction or a particular, right? So you have to take an plane which is perpendicular to motion, and the area that plane sees is what that's how it is defined. But I'll just look up and then let you know if why it is in a particular way. Okay, so maybe I'll stop here today, and then tomorrow we'll try and look at tomorrow we're going to have a tutorial based on this, whatever we discussed so far. So it's going to be in the in MSP, okay, 356.